Hello and welcome to this lecture. So if you remember, we started this week's lectures with three problems, and we sort of derived some expressions for the problem, and we stopped at a point and we said some problems we could solve, some problems we stopped, and we said at this point we need to visualize some expressions that came there. In one problem it was just two linear expressions in x and y. One problem we got a quadratic, another problem we got an exponential, and we said we need to learn about techniques and tricks to deal with these kind of situations. So we are going towards that part of it now. Let's revisit these problems one by one and go back and see if there is a graphical method to attacking them. Okay, so you remember the first question: a shopper is going to buy apples and oranges. The total kilograms, the weight that he wants to buy is 5, and the total cost is 100, and there is a cost per kg, and we wrote this equation. Okay, so here is the solution that we wrote down. It was quite simple. We denoted weight of apples by x, weight of oranges by y. We got these two equations, right? X plus y is 5 and 2x plus y is 8. Okay, how would you graphically solve this? Let me go back to my wonderful all these things now. So let me just get rid of all of these things. Let's try and plot these two equations in Desmos and see what happens, right? So what are the two equations I'm going to try and plot? Let's keep this in the middle. We have to look at x plus y equals 5. So notice this is the x plus y equals 5. The other way to write it is y equals minus x plus 5, right? If you want to write it as mx plus b, y equals minus x plus 5. So that's why you see the slope is minus and then it's shifted up by 5. So x plus y is 5 will have this point. Another way to think about it is x plus y equal to 5 is going to pass through 5 comma 0 and 0 comma 5. So once you identify 2 points on it, 5 comma 0 and 0 comma 5, you simply join those two and extend, right? Straight lines work like that. Once you find 2 points, straight line is easy to draw on the graph, right? So 5 comma 0, 0 comma 5, you just plot this. So x plus y equals 5 is that, okay? The other line is 2x plus y equals 8, okay? So that comes out as a black line here, and this comes out as a green line here. Now, what do I know? So my problem involves two equations and two variables, and I have to solve for x and y, right? X plus y is 5, 2x plus y is 8. The value x, the variable x and variable y has to satisfy both these conditions. So all the x and y that satisfy condition 1 are in the green line, right? And all the x and y that satisfy condition 2 are in the black line. The place where these two intersect, which is 3 comma 2, according to this Desmos calculator, you see that point is the point where both the equations are simultaneously satisfied. So at 3 comma 2, you notice x plus y is 5, right? 3 plus 2 is 5, and also 2x plus y is 8, right? 2x plus y at 3 comma 2 is 8. So this 3 comma 2 is this wonderful intersection point where both of these are satisfied, and that solves this pair of equations. So you see here that if you use the graphical method for solving this, you get that. Okay, so let me just note that down here. X plus y equals 5, 2x plus y equals 8. On the graph, we find x equals 3, y equals 2 as a solution, right? Easy enough, no? So this seems like a very nice simple graphical method. We are able to visualize that and get to the answer. Okay, so that's nice, isn't it? So you see how this graphical technique helps with this function. This is an invaluable technique in all of your problem solving capability. So this one we have done a very simple graphical solution. So he's going to get 3 kgs of apple and 2 kgs of orange, right? So that gives you 1000 rupees, and that also gives you 5 kgs total. So let's go to this farmer problem, and this farmer problem also we had solved up to some point and we got one equation, right? So where is our equation? Here is the farmer problem. If you remember, farmer needs to decide this side x, how big a field he has to cultivate. He's borrowed some money, he's getting some return per square feet, he's spending some money per feet of the perimeter in the fencing, and we got this equation, right? 50x squared minus 400x minus 50,000 equals 10,000. Now in an equation like this, it turns out you can divide throughout by 50 to make your life a little bit easier. So one can do that. So you get x squared minus, you divide by 50, that's 8x, you divide by 50, that's 1000, equals, you divide by 50, that's 200. So these two are the same. So maybe I can try and plot this. Okay, I can even do one slightly better simplification, move the 200 to the left side. I'm going to get x squared minus 8x minus this. But anyway, let me just keep all of these together and plot. So see, because the final profit is 50x squared minus 400x minus 50,000, I want to see when that touches 10,000, right? So this might be a way. Both of these are equivalent. I can see when x squared minus 8x minus 1000 hits 200. Both of these are exactly the same, but if you want, we can also look at that big ugly expression. So we'll start with that and show how all of those things work. Okay, let's go here. Maybe I don't need to plot these two guys. So let's plot this one. Y equals 50x squared minus 400x minus 50,000. Okay. So notice what has happened here. So this is this looks like two parallel straight lines. It's not quite two parallel straight lines. Because of these large numbers, these graphs are sort of going out of whack, right? The scaling is going out of whack. So if you go all the way down, I don't know how much you have to go. So this see, it's so hard to see what this is, right? So this is given the scale, it's very difficult to get everything into one picture and then understand what is going on. But if you go all the way down, you can see that this is actually a parabola, an upward looking parabola. We will see later on how to derive these things. So this also shows you sort of the limitation of the graphical method. Sometimes when the scales go out of whack, you get really thrown off by this graphical method. It's a bit of a pain to understand how it is. You have to visualize. It's better to do something analytically here. But anyway, let me just painfully come down to the bottom of it and then show you that it's actually a parabola, except that the bottom point is like at minus 50,000 or something. So you don't quite see it, but it's actually a parabola. Okay, so let me just zoom. There you go. So now you will probably believe me that it's a parabola if you see at this point. And this also brings out, like I mentioned, the pain of the graphical method. I mean, you should know analytically these are parabola. We know that. So you see the parabola here. But in a different scale, in a different way, you just pretty much see the straight line, right? You're not very happy with that. So here is, if you just zoom it in, you see like it feels like it's a straight line along with the y-axis, but it's not. There is a gap, and that's something that this graph is not showing you. So it's a bit misleading. And I'm also interested in this 10,000 point, right, where the curve touches 10,000. It seems it's touching very close to 0, but it's not exactly at 0. You have to zoom, and let's keep the 10,000 thing here and then zoom, right? And we know this is how the parabola looks, okay? And to help us here, another thing you can do is you can also write down y equals 10,000, right? So you've got this red line, which is the parabola, right, which is actually the final profit, right, 50x squared minus 400x minus 50,000, and y equals 10,000 is the desired profit level. And this gives you a point of intersection, gives you 2 points of intersection, minus and plus. And the plus is what's interesting to you, right? Everything, the x is going to be positive. So the answer it's giving you is 38.871. So if you pick x equals 38.871, you're going to get 50x squared minus 400x minus 50,000 to be equal to 10,000. You can check that analytically if you don't believe me. You put x equals 38.871, you do 50 times 38.871 squared minus 400 into 38.871 minus 50,000, you will get something very close to 10,000. Okay, so this is the size. So the farmer needs to now do, what is our solution for the farmer? This is the first problem, the shopping problem. The second problem, the farmer problem, had another requirement, which is 50x squared minus 400x minus 50,000 equals 10,000, and the graph is telling you that the solution is x equals 38.871, and this will give you this equation to be satisfied. Okay, so this is the solution. This is, I think the units is feet, right? So 38.871 feet, 38 by 38, that's roughly about let's say 40 by 40. We're doing the rough calculation, right? So about 1,600 square feet the person has to cultivate. Small area, it's a very rich crop maybe. So it's getting 10, not that rich, it's getting only 10,000. It's not too bad. Okay, so this is a reasonable solution that we have landed up. And notice a couple of points I want to reiterate again about the graphical method here. It wasn't very easy like the previous straight line one. It had some numbers which were difficult to deal with. Maybe another thing to do which would be slightly easier is, instead of plotting these two guys, maybe I want to plot the other one, right? So the version which I had after dividing by 50. So I had x squared minus 8x minus 1,000. Okay, so this one is a little bit better. You see that the scaling is not too bad, but still it's not that easy, right? So you want to see the whole thing, you can't quite see it. Okay, so anyway, so the value for y was 200, I think, right? So you want to see these two together. You can maybe see it in one zoom. Okay, so there you go. Okay, it's not too bad. Okay, so you see the parabolic shape, and it comes up and it hits 200, and guess what this point will be? 38.871, right? So both of these are perfectly equivalent, and it hits 200 at 38.871, and that is our solution, wasn't it? So a couple of things to keep in mind when you use the graphical calculator. Scale is everything. You see something at a very, very zoomed out scale, everything will look like a line. If you go in, there will be one scale at which you get the correct shape and everything that you want. Why is the scale so important? So it's a complicated answer if you think about it. But we'll come back and see this. The scale issue will come back and haunt us in this course a lot. A lot of things in functions has to be understood at the correct scale. So in some things, a small change can mean everything. In some things, a small change will not mean anything. You have to wait for a long time for something to stabilize. So this happens in circuits as well. In some circuits, some values are very sensitive. You make one small change, and suddenly everything will go for a toss. But some values are not so sensitive. You keep changing them, nothing much will change. So the scale issue has got to do with that also. So some of the values in this coefficients are very large, so things go a bit out of whack, and you should do this. So this tells you the moral of the story, that graphs alone may not be good for you. There is the scale issue. There is this issue of not knowing what to look for. So you have to rely a little bit on analytical methods also. You should know how to deal with these kind of problems analytically. How do you get analytical solutions, and how do you compute them carefully? That also plays a role. But anyway, we have solved the second problem as well. At least graphically we have solved it. We've got a answer. Let's go to the third problem that we had with us. Let me start with the third problem here, which was this bank deposit problem. We deposited 1 lakh, and we wanted to compare returns under simple interest and compound interest, 10% simple interest and 1% compound interest. And once again, this problem also we had solved, or at least written up equations. I wrote a lot of laborious, painful equations to show you this iterative nature of the computation. And whenever you have this iterative accumulation with multiplication, take a fraction of what's already accumulated and add it to this, you get this exponential behavior, right? So that I think is a crucial idea, another idea for you to ponder over, where this exponentiation comes from. You have some deposit, you take a part of it and add it on to itself, and then deposit it again and repeat. So that when you do that iteration, you'll suddenly have this exponential behavior. And this is, so we saw this problem where we calculated the simple interest with 10%, and then we calculated the compound interest very slowly to show you the exponentiation, and we saw it came to around 4060, 4.06%. And then there was a second part of the question which said, what rate of compounding, quarterly compounding over 1 year will give you the same interest as simple interest of 8%? How do you do that? So you have to now have an R% per quarter compound interest, and then you see that the total amount is D times 1 plus R by 100 raised to the power 4. If you have, of course, X quarters, then that X will show up in the exponent. And then the interest earned in 1 year is, you have to subtract the D from that. So you get this formula, and then we saw simple interest is RS percent, and you got a certain interest earned. You equate these two, you finally end up with this equation, right? So let's see if we can solve this equation graphically. 1 plus R by 100 raised to the power 4 equals 1.08. Okay, so let's do that. Let's go to our Desmos. We probably don't need these two. 1 plus x by 100 raised to the power 4. Okay, so that's the graph that you get here, and then y equals 1.08. Okay, notice once again we are getting some sort of a scale issue, right? At this scale it looks like everything is 0 or something. So once again you have to zoom in. I'll tell you another trick here which you have to pay attention to. So notice here, finally we are seeing between the black line and the red line there is an intersection. So you can zoom in, zoom in, zoom in, zoom in. There you go, and then you can go see what that point is. 1.943, comma 1.08. So that's what the graph tells you. And we had to do some zooming. It was not too easy. So that's the bank interest solution, right? So the bank interest banking problem had this 1 plus R by 100 raised to the power 4 equals 1.08, and the graph is telling you that, sorry, let me just write R. Okay, so there we wrote X, here we are writing R, both of them are the same, 1.943. Okay, so a 1.943 quarterly rate will give you 8% annual rate. So the compounding gives you an advantage, right? So if you were to give you 2% per quarter, that is the same as 8% per year, simple interest, right? Approximately linear behavior. Here you have an exponential behavior. Because of that, 1.943 is enough to give you an 8% simple interest at the end of it. Okay, so this is the calculation. I hope this is clear to you. Let me go back once again and comment on what happened here. Let me just put this all together. So we see that all these problems, we got equations earlier with our mathematical approach of assigning variables and finding relationships. We got a relationship which we had to solve. We didn't know how to solve. We stopped there, and now we have a graphical solution for this. In some cases, when the numbers are nice to handle, we got very clear, simple graphical solutions. So we are seeing when the numbers become different, the graphical solution sometimes needs the correct look at scale. The scaling is very important. You have to pay attention to how the numbers work. Otherwise, everything looks like a flat thing, right? So I showed you how that works. But still, we were able to get all the answers. We did solve all of them with the help of Desmos. But the precise nature of the answers, an easy way, mechanical way in which you can get it, graphs sometimes are not immediately obvious, right? So or you may not have access to a graphical calculator sometimes, right? You may have to do it by hand. So it's good to look at analytical methods of how to go about solving these things. Okay, so in this week's lecture, we will at least see a little bit of the first type of problem and the second type of problem, and how to think about analytical solutions for these two problems. Okay, so we'll do that in the next lecture. In this lecture, hopefully you understood how when you end up with expressions and you have to solve them, you can always take the help of a graphical calculator, at least understand how the nature of the solution is. You have to pay attention to scaling. You may want to alter the scaling. You may want to change the coefficients a bit, redefine some variables to get good scaling. You can do all that. But once you do that, you will get a solution here. But maybe analytical methods are also very interesting going forward. Okay, so with this, I'll conclude this lecture. Thank you very much.